Hello and welcome to our lesson on building quadratic models. This is going to be from section 3.4 in our Precalculus text. In this section, we're going to be looking at word problems, application problems that result in quadratic functions, either through verbal description, through how the problem explains the scenario, or from a set of data. Now, I think the best approach to teach this particular section is going to be through example, so we're going to look at several examples of how to do this. In our first example, we have the marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by the demand equation X equal 21,000 minus 150p. So that piece of information is given. There are a couple of other things we need to extrapolate from the problem. First of all, it says the price of P dollars per unit is going to be the cost of a calculator. So we're going to make a note of that P is the price per item. And here the item is a calculator. I'm going to use generic terms and say P is the price per item. We're also given the number X of calculators sold. So X is going to be the number of items sold. And if we read part A, it says find a model that expresses the revenue R as a function of the price. So if you think about what revenue is how much money you make. And that is calculated by multiplying the cost per item times how many items you sold. So we can come up with the revenue equation. The revenue equation is going to be the price per item multiplied by how many of the items you sold. And then we simply need to express that as a function in terms of P. Okay, so for the answer for part A, as a function, the revenue in terms of P is going to be P times X, but we can replace X with what they gave me. So we're going to do substitution in order to get this function in terms of P, and then we do need to simplify. So again, the revenue function, if I distribute the P, is going to be 21,000p minus 150p squared. And that's going to do it for part A of this problem. For part B, it says what is the domain of R? So we're going to find the domain of the revenue function. It says assume that the revenue is non-negative. So it wouldn't make sense to talk about a negative revenue. So the domain of the function is going to depend on having revenue values greater than or equal to 0. So to answer this part, we're going to let the revenue be 0. And then what we're going to do is we're going to solve for P. So to solve this particular quadratic equation, since there are only two terms, they do have a common factor of P. What we're going to do is factor out a P, leaving us 21,000 minus 150p, and then set each factor equal to 0 and solve. So P equals 0 would be the lowest value that we would want to set the price of a calculator, although that doesn't make any sense to make your calculator not cost anything. And for the second factor, if we solve for P, moving the 150p to the other side will make it positive 150p equals 21,000 divided by 150 is going to give me the maximum value for the price of a calculator, and I'm going to use my Casio to calculate this value. So we've got 21,000 divided by 150 is 140. So I've got my lowest cost and my highest cost. Anything outside of these values would produce a negative revenue. And so now we can write the domain of our function. It's going to be the set of all p's such that p is greater than or equal to 0, but less than or equal to 140. Or if you want the domain in interval notation, we would say the domain is everything from 0 to 140. And you need to be prepared to give either set notation or interval notation. Part C, what unit price should be used to maximize revenue? So here we're looking for the price we need to set the calculators at in order to maximize our revenue. Now there's a couple of key characteristics that are going to help us come up with this solution. First of all, if you notice the coefficient of p squared is negative, we know that every quadratic makes a parabola, and if the value of a in this case is less than 0, what we're going to have is an upside down parabola where the maximum value will occur at the vertex. So a nice thing to know is when you're dealing with quadratic functions and they want you to either maximize or minimize, they're really asking you to find the vertex. And we know the formula to find the vertex of a quadratic function is minus b over 2a f of minus b over 2a. The x-coordinate of the vertex in this case, if we scroll back up and look at our function, notice that p is where x normally is. So the x-coordinate of our vertex will represent the price that gives the maximum revenue. And the y value will give the maximum revenue. It'll give the dollar amount that we're going to make depending on what we set the price at. And so now all we need to do to answer part C is plug and play. So we know A is negative 150, B is 21,000, so that's going to give us negative 21,000 divided by 2 times negative 150, and then f of whatever we get, that will give the maximum revenue. So again, pulling up our calculator, we're going to have negative 21,000 over 2 times negative 150. 70. Now that's going to be price. That's going to be the price that we need to set the calculators at in order to maximize revenue. So the answer for part C, P equals $70. Part D, if this price is charged, what is the maximum revenue? So part D is going to depend on us finishing the vertex formula. Knowing that we're going to plug in 70 into the function and work it out to get the maximum revenue, we're going to bring up our handy-dandy calculator and input that calculation. Now the function was 21,000 p minus 150 p squared. That's plugging in 70 into the revenue function, giving us $735,000 as our maximum revenue. So the answer for D, right there, that is our maximum revenue. Part E, how many units are sold at this price? Well, if we scroll back up just a bit, it says the number of calculators sold is given by this equation. So we can plug in for P and calculate how many calculators are sold. So here we go. X is the number of calculators sold. Plugging into that formula, that's 21,000 minus 150p. Again, using our calculator, 21,000, just to make sure we don't make an arithmetic mistake. We're going to get 10,500 units sold. Let's call that calculators sold. That's how many calculators we're going to sell if we price the calculators at $70 a piece, giving us a maximum revenue of $735,000. Part F, Graph R. I think we have enough information to graph R with what we've already determined. So what we know is that we're going to have a coordinate system like so, X and Y, but remember X and Y in this case are P and R of P, where the lowest that we would set the price to is $0, and we calculated the maximum price to be $140. Now, of course, one of the things I could do is I could, with my function, make a table of values and generate some ordered pairs. I do intend to do that with the minimum and maximum value. So for the first value of P, if I replace both P's with 0, that's obviously going to give a 0 because every term has a P, which is going to give us a point at the origin. And then if I plug in 140 for P, remember back up here where we did this work? We know that if we plug in 140 for P, that's going to produce a revenue of 0 as well because it was a solution to the equation. All right, so what I now know are both of the x-intercepts. Remember, we also have the vertex, which I can plot, knowing that the x-coordinate, which in this case is P, is 70. That falls halfway between 0 and 140. I know that that is the highest point on the graph at $735,000. So that's going to give us an ordered pair up here. So then I simply connect the dots, making a parabola, and that gets the graph of the function. And for the last part, part G, it says what price should TI charge to collect at least $675,000 in revenue. So looking at the graph, knowing that $675,000 is lower than $735,000, we want to make at least that much money, which means that there's going to be two prices, call it P1 and P2, that I'm going to need to stay between in order to keep those profits above $675,000. Now the question is, how do I find those values? Well, remember this is a y coordinate. The $675,000 is y. I need to find x. So that means we're going to have to plug into our revenue function, replacing R of P with $675,000 and then solve for P. All right, so here's our equation set up and ready to solve. Knowing that I need to have the squared term positive and that I have to set a quadratic equal to 0 and solve, we're going to be moving these two terms over, giving us 150p squared minus 21,000p plus 675,000 equal to 0. And then I think we can reduce the terms to make this easier to solve by dividing both sides by 150. And that's going to give us p squared minus 140p plus 4,500 equals 0. And then even this is going to be tough to factor. I guess we could complete the square. So this particular setup is actually easy to complete the square. So we're going to demonstrate solving this quadratic with completing the square. First, to complete the square, you have to move the constant to the other side. And that's going to free up a space for us to come up with a new constant that we're going to add to both sides. Now, the way you determine that number to complete the square is you take the coefficient of p, cut it in half, and then square it. So negative 140 divided by 2 squared is 4,900. That is the number we need to add to both sides in order to complete the square. And now we know that this trinomial is going to factor as a perfect square trinomial with this sign and the square root of the 4,900, which is 70. And then on the other side, I need to do the math. 4,900 minus 4,500 is 400. And then I can take the square root of both sides. The square root of 400 is 20. Don't forget you need a plus or minus 20. Square and a square root cancel, giving me p minus 70. And then dropping the 70 on the other side will give us 70 plus or minus 20. 70 plus 20 is 90. 70 minus 20 is 50. And these are the two prices that we need to stay between in order to keep our revenue at 675,000 or greater. And that's going to finish it up for this particular example. All right, next example. We have a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So key points here, we have 2,000 yards of fence to build a rectangular enclosure. So knowing that we're going to build a rectangular enclosure, here I've got my rectangle constructed. There are some things we know about a rectangle. First of all, in a rectangle, you've got length and width. We also know the formula for the perimeter of a rectangle, which is 2L plus 2W. And we know the area of a rectangle is length times width. So the fact that we have 2,000 yards of fence means that the entire perimeter will be 2,000 yards. And if they want the most area, what they're really asking us to do is maximize area. Okay, so first step, we're going to take our perimeter formula and replace P with 2,000. So that gives us a formula with length and width. And then what I'm going to need to do is I'm going to need to solve for either length or width so that I can substitute in the area formula and get the area in terms of length or width. So I choose to solve for L. So I'm going to minus 2W from both sides. That's going to give me 2,000 minus 2W equals 2L. And then dividing through by 2, we can see that the length is 1,000 minus W. So once I know what L is, I can come to my area formula, substitute for L, and we will have the area as a function of W. So here we go, substituting for L. That's 1,000 minus W times W gives me an area function of 1,000 W minus W squared. Again, that is my area formula, but as a function of the width. And then remember in the previous lesson I said anytime that you want to maximize or minimize a quadratic function, you need to find the vertex. So our vertex formula is minus b over 2a. In this case, b is 1,000. A is -1. That's going to be minus 1,000 over 2 times -1. And then f of, or in this case a of, whatever that is, will give us the maximum area in square feet. So the x-coordinate of the vertex, this calculation is going to give me the width that gives the maximum area. That's going to be 500. And then if I plug in to the function, replacing each w with 500, that will give me the maximum area. Now, I don't know if they asked for it, but we're going to go ahead and calculate that just in case we need it. That's going to be 1,000 times 500 minus 500 squared. 1,000 times 500 minus 500 squared. 250,000. 250,000 square feet will be our maximum area. So if we reread the problem, it says, what are the dimensions? Well, the dimensions are the length and the width. So we have the width. What we need to do now is plug in and calculate the length. So the length that will give the maximum area is 1,000 minus 500. Look at that, which also works out to be 500. And so the dimensions would be 500 by 500. And you can put the little tick marks there if you want to designate feet. These are the dimensions that will yield the maximum area. And that's going to do it for this particular example. Next example, we have the Golden Gate Bridge, a suspension bridge, spans the entrance to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended from two huge cables more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. The cables are parabolic in shape and touch the road surface at the center of the bridge. Find the height of the cable above the road at a distance of 1,000 feet from the center. So here I've constructed a picture that represents the Golden Gate Bridge. Notice that I placed my coordinate system in such a way that the vertex is located at the origin. If you do that, that will make your calculations, finding your quadratic function, super easy. So filling in on the picture information that we're given, we know that the towers are 746 feet tall. So we're going to label a tower here 746 feet. We also know that the road surface above the water is 220 feet. And we're given that the towers are 4,200 feet apart. Since we located the vertex at the origin, that's going to split that distance in half. So the distance from the center of the bridge out to a tower is going to be 2,100 feet. Now, all of this information is needed so that we can calculate another point on the parabola. Notice we do have the vertex, which we located at the origin. I would like to have another point on the parabola so that I can find the quadratic function for this scenario. So, the distance to the top of the tower from the roadway is going to be the difference of 746 and 220. So if I do the subtraction, I'll have the height of the tower from the roadway. And we're going to use our handy dandy calculator for that. 746 minus 220 gives us a height of 526. So this height here is 526 feet. And so now I know that this ordered pair is going to be represented by the distance to the tower from the origin, which is 2100 feet, and then the distance from the road up to the top of the tower, which is 526 feet. Again, now that I know the vertex and a point on the parabola, I can construct the quadratic function. So starting from the vertex form of a quadratic function, we know h and k are 0 and 0 because h and k is the origin. And we know f of x is y. So I do have an x and a y that I can substitute, and that's going to allow me to find the value of a. So doing a little plug and play, we've got 526 equals a times 2100 minus 0 squared plus 0. Simplifying, that's going to give me 526 equals a times, that's going to be 2100 squared, and then if I divide both sides by 2100 squared, I'm going to have my value of a. So a is 526 divided by 2100 squared. Plugging that back in to our quadratic function, knowing that x minus 0 is just x squared, and the plus 0 is going to disappear, is going to give us a simplified quadratic function of f of x equals 526 divided by 2100 squared, x squared. So I cleaned up my picture a bit so that we can answer the question they actually asked, which is to find the height of the cable above the road at a distance of 1,000 feet from the center. So if we go from the center over a distance of 1,000 feet, what we want to find is the height of the cable at that point. Now this is going to be another ordered pair on the graph, knowing that x represents the distance over and y is the height. And so this is going to be a simple plug and play problem. Given that x is 1,000, we're going to replace x with 1,000 and calculate the height. So that's going to give us 526 over 2100 squared times 1,000 squared. And we're going to calculate that with our handy dandy calculator. 526 over 2100 squared times. Now you can either do times or you can do parentheses. Either way is fine. 1,000 squared is, and let's go ahead and round that to the nearest whole number. It doesn't specify in the problem where to round to, so I'm going to choose to round to the nearest foot, which will give us a vertical height of 119 feet when we are 1,000 feet from the center. And that's going to do it for this example. Next example. Here we have a word problem. It says the data in Table 8 represents the average annual expenditures for consumers of various ages in 2016. Part A, they want us to draw a scatter plot of the data. So that just means to plot the data as ordered pairs, where X is the age and Y is the average annual expenditures. Of course, you could plot these by hand on a hand-drawn graph, but the easiest way to get a nice graph, in my opinion, is with Desmos. And we're going to hit the plus sign and use the table feature. So this will allow us to input our table just the way it looks over here in Table 8. So now that we have our data entered in our table, I don't see any of the ordered pairs, so we're going to have to manipulate this window so that we can see the points. And the nice thing about Desmos is you can scroll your mouse wheel and click and drag. to edit the graph. Much easier to manipulate this window than it is to on a TI-83 or an 84 graphing calculator. And so that gives us right there a nice picture of what our scatter plot looks like. Now, not only do they want us to draw a scatter plot, but they also want us to comment on the type of relation that exists between the age and average annual expenditures. And looking at how this data is plotted, to me it looks like a parabola that opens down. So we would expect there to be a quadratic function that would approximate this data set fairly accurately. And again, as far as answering this question, to draw the scatter plot, again, you can draw that by hand. You can use graphing paper. I don't see any reason why you wouldn't be able to use Desmos to get an appropriate estimate of what the graph looks like. Part B, use a graphing utility. I think they're referring to a graphing calculator to find the quadratic function of best fit that models the relationship between age and average annual expenditures. So again, notice that they are asking us to find a quadratic function that best fits this data. And you can use a graphing utility, but what we're going to use is our Casio that I normally use in my videos and show you that it does this just as well. Okay, so to come up with our quadratic function that best models this data on our Casio ClassWiz, we're going to start by going to the menu, and we're going to go down and over until we get to the Statistics tab and hit equal to select. Notice that option 3 is a quadratic, so we're going to click 3. And then, just like we did in Desmos, we're going to enter our data from our table into the Casio. So once we've got all of our data input into our Casio, in order to get the quadratic function, then we're going to go to option right here, and we're going to go to the regression calculator number 4. And notice that is going to give us our value for A, B, and C for our quadratic function. And I realized that that screen was way too small to probably read in the video. So what I did is I did a screenshot and blew that up, hopefully big enough for you to see. I do want to point out that the way this calculator is displaying our quadratic function, A is the constant, B is the coefficient of x like normally it would be, and C is the coefficient of our x squared. Notice, if you know anything about quadratic functions, you're going to know that the coefficient of x squared, if it's negative, causes the parabola to open down. And so this makes us feel good about our calculation, knowing that the data modeled an inverted parabola. So what we're going to do is we're going to input this equation into Desmos and see how well it fits the data. Here for part B, I have written the function using function notation, and that's going to take care of part C, where part C says use the model found, and the model is the quadratic function. In part B, to approximate the age at which the expenditures is the greatest. Now keep in mind, anytime they want to know when something is the greatest or the least, that's the same as asking you to maximize or minimize, and that means that you're going to need the vertex. So once we get this graphed in Desmos, it'll be really easy to come up with the vertex, and we can approximate the age at which the expenditures are the greatest. And here we are at Desmos. We've got our function entered. Notice the function is represented by the blue graph. The red dots are data from table 8, and you can see that the blue graph does fit really close to the red dots. And then to answer part C, if we simply click on the blue graph, we can see the vertex and estimate the age at which the expenditures are the greatest, and it looks like that's going to be at age 50 years old. Part D, use the model found in Part B to approximate the highest average annual expenditure. That's again going to be the vertex, but here that's the y coordinate, because in our table the average annual expenditures were the y's. So all we have to do is go back to Desmos, pick the y coordinate of the vertex, and we're going to have that approximate value. And back to the graph, we can see rounded to the nearest whole number, that's going to be 70. That is in thousands of dollars. So that would be $70,000. And part E, use a graphing utility to draw the quadratic function of best fit. We've already done that using Desmos. And so that's going to do it for this particular example. And that's also going to do it for this lesson. So if you have any questions or comments about anything that I've covered, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.